today we're going to be looking at elastic potential energy. Now, this is just like our other types of energy, like kinetic energy or gravitational potential energy, where you are storing energy in a certain way. In this case, what we're going to be doing is we're going to be storing energy by changing the shape of something. So if I take, for example, this pen lid here, okay, I can peel this back here, and there is now energy stored in this, because when I release it, that energy is going to get transferred back initially into kinetic energy, and then ultimately as heat energy in the surroundings, because it's now stopped. But I've stored elastic potential energy, and I can release that energy, okay? Now, the way we calculate elastic potential energy is using the following equation, okay? So elastic potential energy, so we say energy of the elastic type is given, and it's very similar to the kinetic energy equation, is half times by something called the spring constant times by the extension squared. Okay, now depending on at what level you are and what exam board you use, this will sometimes be an X. At A level we use an X in general, but for some reason GCSE they tend to put an E in, so I'm going to use an E for today. I will try not to flip back to X, which sometimes becomes a habit of mine, but I'm going to follow it through with an E. So we've got elastic potential energy. This thing here is called the spring constant. And this here is our extension. And I'm also just going to write / compression here, okay? Right below, because in terms of the equation, if a spring is squashed or if it's stretched, it's gonna we treat it the same way, okay? If it's been squashed by 5 centimeters or if it's been stretched by 5 centimeters, the equation works the same. Now, this thing here, the spring constant, this is just a number that tells you how stiff the spring is, okay? It actually tells you how many newtons of force it would require to stretch that spring by 1 meter. So a big number here, a large number for the spring constant, means that it takes a lot of force to stretch that spring, okay? So it's got a high spring constant, it's a stiff spring. If it's a very small number, it requires not so much force to stretch the spring, so it's a much looser and much easier to stretch spring. Hey, your extension is, no surprise, going to be measured in meters, and your energy is going to be measured in joules. Okay, now something that we have to be aware of when we're thinking about this is that we have to assume here that this is a regular spring that's going to obey Hooke's law, okay? Now that is a whole other lesson, okay? There is a whole other lesson, there's a whole practical on how do we find out what K is. Very, very briefly, we pretty much have to stretch a spring and measure how much force it requires to stretch it by a certain amount. And if this spring, if the spring that or the item that you're stretching gives you a straight line on this graph here, certainly up to some point where it might do something different, then it obeys Hooke's law, and it means that this value here, this spring constant, is actually constant, okay? We're going to look at that another time though. I'm not going to deal with that too much. If you wanted to find it, all you would have to do is find the gradient of this line here, okay? But I'm going to come back to that a different day. Now, let's look at extension first of all. Now, it may seem obvious, but something that a lot of people often get wrong is this extension. Now, if I was to draw a spring here, okay, which would look something like this with my amazing artwork, okay, and then I was to stretch that spring, we need to know exactly what is the extension, where do we measure it. Now, so long as you're measuring from 2 fixed points, okay, I tend to measure from this point here. Oops, let's make sure that's in line. I tend to measure from this point here to this point here because that's where the actual spring is. Now, if I said that there was my initial length, okay, we'll call that L1, and then I could say that this would be my new length of the spring, L2. It's the difference between these is our extension. So the extension is how much it has actually increased its length by. Okay? So if I said to you that L1 was equal to 2 centimeters, and if I said that L2 here was equal to 10 centimeters, then my extension is going to be equal to 8 centimeters, which in a calculation I would need to put as 0.08 meters. Okay? So let's look at some calculations. Let's look at some things we can do. Let's use this exact spring here. Okay, I'll leave that on the board there. Actually, I can probably fit around it. And let's work out how much energy we could store in it if we said, for example, that the spring constant was equal to 25 newtons per meter, which is like the ones that I have in school that I normally use. So if I wanted to work out the energy, I'm going to say that the elastic potential energy is equal to half, I'll write 0.5 now because that's what I'll put in the calculator, times the spring constant, which is 25, times by 0.08 squared. Okay, right, another slant there. Okay, so half times 25 times by 0.08 squared. Okay, we put this into our calculator. Okay, 0.5 times by 25 times by 0.08 squared. Loads of people forget the squared, loads of people forget the half. Don't be one of those people. And we get, oh, that's amazing, 0.08. Okay. I almost don't believe that, but the calculator says it is. And we therefore need a unit to this, and the unit is going to be joules. Fantastic. Right. So that would be the amount of energy that is stored in the spring there. Okay, simple as that. Let's look at rearranging this equation next. Okay, so this question here says, calculate the spring constant if 2.4 joules of energy are stored by a spring that is stretched by 5 centimeters. Okay, so the first thing that I'm going to do, and if I'm ever doing any kind of exam, literally the first thing I do on any of these questions, before I even realize what I've got to calculate, I'm just going to look at that and I'm going to say this is 0.05 meters. That's fine, that's in a unit that I like. Okay, right, so I need to rearrange this equation. So this equation here, I am trying to find, well, they've given me the energy, they've given me the extension, I am trying to find the spring constant, okay? So you could, you should really just be able to rearrange these equations by doing inverse operations, okay? I could bring the half, so this is 0.5, I could bring the half down, so I'm dividing by a half or timesing by 2. And I could bring the extension squared down, divide by extension squared onto the other side, and it would leave me with k on its own. Okay, I'm just going to show you the triangle method because a lot of people use that as well. So if we write this equation triangle, I've got a feeling maths teachers probably won't like me for this, but it works. So the energy is on the top because the others are all times by each other. So I've got 0.5 times by the spring constant times by extension squared. And if I want to find the spring constant, I cover that up with my hand, and I would say that the spring constant is equal to the elastic potential energy divided by, and then I've got the other two things down here, 0.5 times by extension squared. Okay, and again, if you a very, very important trick here is to make sure when you're then doing this calculation, you're using the divide button on your calculator. Okay, so that's the button that looks like this on most calculators, because if you do this, it means that these two here on the bottom, if you put those two in here, it's going to treat that almost as though they're in brackets, okay, because it's the bottom half of that fraction. Okay, if you were to type into your calculator, if we put the numbers in now, if you were to type in, I'm going to do it in red because it's wrong. If you were to type in 2.4 joules divided by 0.5 times by 0.05 squared, even though you've got the numbers right from the question, this is going to give you the wrong answer because your calculator is going to do this bit first and then it's going to times your answer by 0.05 squared. You cannot afford to be losing marks like that. So you need to make sure either that you are putting brackets around this here or doing this part first. Okay, if you're doing it on an old calculator or on a rubbishy phone calculator, you do this bit first, okay, and then do the energy divided by your answer to that, or just use the fraction button on your calculator and it will make sure it gets it all right for you. Okay, so if we do this properly then, we're going to say 2.4 joules of energy all over 0.5 times by 0.05 squared, and I'll put the brackets there just to make it clear. And if we type this into our calculator now, okay, so I'm going to press my brackets button first. I'm going to put 2.4 in on the top. I'm going to put 0.5 times by 0.05 squared on the bottom, and this one gives me 1920. Okay. And this is our spring constant, so it's going to be measured in newtons per meter. Okay. The other way we could rearrange this equation is if we were trying to find the extension. Okay, so let's try this one. Okay, so this one I've said calculate the extension if 1.5 joules of energy, so I've got 1.5 joules of energy, are stored by a spring that has a spring constant of 80 newton meters. Okay, so this time what they've given me here is they've said you've got a spring constant, you've got an energy, and I'm looking for the extension. Okay, so I'm going to do the same thing again. I'm going to use the triangle method again to rearrange the equation, but this time, okay, we've got our elastic potential energy on top again, 0.5 spring constant extension squared. Now you'll notice that the extension obviously here is squared. So what I'm going to do is, if I use the triangle, if I cover this up, okay, I'm actually covering up extension squared. So extension squared is what the triangle is going to give me. So extension squared is equal to elastic potential energy divided by half the spring constant. Okay, so if I want to actually get extension now, I need to square root this. The square root extension squared will give me extension. So I'm going to say the extension is equal to the square root of elastic potential energy over half times by the spring constant. Okay, so if I do this in my calculator now with these numbers, I'm going to be saying for these numbers here, I'm going to be saying the extension is equal to the square root of 1.5, which is my energy, over half 0.5 times by 80. Now again, if you've not got access to a scientific calculator, then you need to be doing this bit on the bottom here first. 0.5 times 80 is 40, then do the 1.5 over 40 and square root it. But I'm going to do it all in one. I'm going to press my square root button, I'm going to press my fraction button, I'm going to press 1.5 on the top, 0.5 times 80 on the bottom. I'm going to check all my units, I'm happy with those, okay? And this is going to give me 0.193649, loads of decimals. Ultimately, it gives me around about 0.19. So it's going to give me 0.19 meters, which if I wanted that in centimeters is obviously 19 centimeters. But I would probably be happy with the answer in meters there. Okay? Right, the final thing we're going to do with this is we're going to look at how we might link it to another type of energy. Okay, so we've just looked at this one type of energy so far, but what if I said to you I had a spring and I stretched that spring by a certain amount and I wanted to know how fast it might fly off or how high it could travel, something along those lines. So let's have a go at that. Okay, so the question I've got here says this: A spring of spring constant 30 newtons per meter is stretched from an initial length of 4 centimeters to 22 centimeters. As I'm going through this, by the way, if I'm sitting this in an exam, before I even get to the rest of the question, I'm writing above here, 4 centimeters is 0.04 meters, 22 centimeters is 0.22 meters, okay? I automatically am going to do these conversions as I go through, okay? It's then fired vertically up in the air, okay? So you can imagine stretching a spring, firing it vertically up in the air, okay? Calculate the maximum initial speed, so the maximum speed it will be fired with, and calculate the maximum height that it could reach. So the way we're going to do this question is we're going to work out how much energy is stored in that spring, and then we're going to assume that all of that energy is converted into kinetic energy as it's released, okay? And then we're going to work out the speed here, or we're going to assume that all of that energy is converted into gravitational potential energy as it's fired up into the sky. And we'll be able to work out the height, okay? The other thing that we will need to use in this is we are going to need to know the mass, and we're also going to need to know the gravitational field strength, which I realise right now that I've not given you. So I'm going to write those down too as well. We'll just say here that gravitational field strength is, we'll use 9.8 newtons per kilogram. And I will also say that the mass of the spring is going to be, we'll say it's 20 grams, okay? So 20 grams, I'm just going to convert that 0.02 kilograms, okay? I should have given you those at the start as well. Now, so let's do some of these calculations. First of all, we need to work out the amount of energy stored in the spring. So first of all, I'm going to say the elastic potential energy is 0.5 times by the spring constant, 30, times by the extension squared. Now my extension is actually 18 centimeters, okay? From 4 centimeters to 22 centimeters, 18 centimeters, or 0.18 meters, and that is going to be squared. So let's work out what this is. So 0.5 times by 30 times by 0.18 squared is going to give you 0.486, okay? Joules. Now it might be tempting to round that to probably 0.5 joules at the minute, but I'm not going to do that because I need to use this number for future calculations. And if you're going to use a number for future calculations, you have to use the whole number, the raw number. You can't round it and then use it because you are going to your error might mean that you're going to get an incorrect rounding error later on, okay? So this is the amount of energy that's stored in this spring. Now if I want to release that spring, if I say all of that is converted into kinetic energy, let's plug it into a kinetic energy equation. So I'm going to say that basically my 0.486 joules of energy is equal to, and we have to try and remember our kinetic energy equation, which is half times by mass times by speed squared. Okay, now we know that the mass, because I gave it here, is 0.02 kilograms. So this is equal to 0.5 times by 0.02 times by v squared. Now you could take this step by step, or you could rearrange the equation straight from here. Okay, I like to rearrange the equation all in one step, using either the triangle method or just doing it, okay? This one's going to be a square root one, a little bit like the finding the extension from the elastic potential energy equation. But let's do this one without doing that. Let's do it a step at a time with the numbers already put in. It's just a different way of doing it. So here I'm going to do this bit here, 0.5 times by 0.02. So I'm going to say that's going to be 0.01 times by v squared, and that's equal to this still. Now I'm going to divide by this over here to get v squared on its own. So I'm going to say, we'll get down on my knees here. So I'm going to say 0.486 divided by 0.01 equals v squared. Okay, you could work that out, or you could just then say that the square root of that is then equal to v. So let's do that on our calculator. Okay. So the square root of 0.486 over 0.01 is equal to a speed of, again, it's a long number here, but it's 6.9713 something. So I'm going to say this is equal to 6.97. You could give it, okay? You should probably round this to two significant figures, but we'll leave it at that, okay? So 6.97 meters per second, okay? And this is how we're going to work out the speed. We're just going to say that the elastic potential energy is equal to the kinetic energy, and then rearrange our kinetic energy equation. We're going to do the exact same thing for the gravitational potential energy. So this was for A. For the gravitational potential energy here, okay, this time, instead of saying that this amount of elastic potential energy is equal to kinetic energy, I'm going to say it's equal to gravitational potential energy. So this time I'm going to say my 0.486 joules of elastic potential energy is equal to the mass times by gravitational field strength times by the height, because this is our gravitational potential energy equation, which is equal to 0.02 times by 9.8 times by the height. Okay, no square rooting or anything in this one. I've got these two are going to come over here, so we're going to say 0.486 over, I'm going to bring both of these down, divide this side by both of these, so 0.02 times by 9.8, and that's going to give me the height, and it's as simple as that. We work that out. 0.486 over 0.02 times 9.8 equals 2.47959. So let's round that to, we'll do three significant figures like the last one. So this is going to be 2.48 meters. And it's as simple as that. Okay, so we're using this equation here to work out the elastic potential energy, and we can, in any situation, we can convert this into another kind of energy that we've dealt with. There's loads of different ways you could do it. You could, I mean, if you wanted to, you could probably say, if you had a spring that had a certain amount of elastic potential energy in it, you could then hold that underwater, you could release the spring, that's going to be converted into kinetic energy, which is ultimately going to be converted into thermal energy or internal energy in the water. You could probably then use a specific heat capacity equation and work out the temperature increase of the water. You could do any kind of equation that involves energy transfers, okay, if we're assuming that all the energy is going to get transferred from elastic potential into the type of energy that you need to deal with, okay? So I'm going to leave it at that, and hope that's helpful.